Hello. In today's session, we'll discuss the topic of type of functions, in which we'll see the different type of functions and their graphs, and try to understand what small changes can help change the graph and what nature it can change up to. So let us start with the first one, which is linear function. So the first type of function we are going to discuss is linear function, and in which we can see that the general form or the general standard equation which we come across is y equal to mx plus c, where this m is going to be the slope of your graph and this c is the constant which can be said to be intercept. Now we'll see the different nature of graphs and the changes and transformations which are possible. Well, this is the first graph we'll start with for a linear function, and we call this as identity function. And we can clearly see that y and x are having a very respective value. Like for x equal to 1, we will have y equal to 1. For x equal to 0, we will have y equal to 0. For x equal to minus 1, we'll have y equal to minus 1, and so on. So this is the respective value of y for the different value of x. And of course, we can see that the x value can move from positive to negative end, and for that we are also getting the y values to be positive and negative. Now we have a different graph, the second function, which is g, where y is equal to 2x, so that we can see that the slope has increased to 2 from the first one as 1. So with this we can see that the slope increases and the respective values of y for different values of x has also started increasing. Similarly, the x will have more negative values of y once we go to the negative side of x. Now, this is the third graph we have, that is h, where y is equal to 0.5. Now, in this case, we can see that the slope has gone down, and we'll see that for respective values of x, we'll have lower values of y. Like, for example, if we say that x is equal to 10, we have a lesser value of y as maybe 5, and y equal to x gives 10, whereas y equal to 2x gives 20. So, this is happening on the other side of your x-axis also. So now in this case we can see that the lower the slope, the lower the values will come down, and in that case this is how the slope changes the graph. Now in this case we'll see that the transformation of the graph, like in this case the first graph which was y equal to x, now the second graph is y equal to x plus 2. So with this we can see that there is an uplift of the graph by 2 units. So whatever value we were getting for x equal to 0, now we are getting x equal to 2, and for the respective values of x on both the sides, we can see that the y value will be just plus of the value what we were getting in the, for the respective values of x, we will get plus 2 of what we were getting actually for the function f. Now this is the third line we are drawing here, the linear equation which is of the form y equal to x minus 2. So with this we can see that the graph which was originally there as y equal to x has just shifted down by 2 units because of this minus 2. So for all the respective values of x, now we will be getting 2 units less. Like for x equal to 0, we had y equal to 0, but now it will be equal to minus 2. So this is how the transformation is changing the graph here. In this case, we see the function has y equal to negative x as g function, and we'll get right opposite values of what we were getting in the first equation, that was f y equal to x. So if initially we were getting y equal to 2 for x equal to 2, now we are getting y equal to minus 2 for x equal to 2. So that negative slope is just making the graph going down with the increasing value of x. Now we will see some of the polynomial equations which we generally come across, and the standard form, we know that y will be equal to a to the power of n x to the power of n plus a to the power of n minus 1. The general form of polynomial equation is going to be y equal to a n x to the power of n plus a n minus 1 x to the power of n minus 1, and it goes up to a naught x to the power of 0, which is nothing but a constant of the form plus c. Now if n, where n is going to take all the integral values or the natural values, of course being non-negative. Now if possibly we get something with n equal to 2 as the highest one, then we can say that the equation is quadratic. For n equal to 3, we can say with n equal to 3, we will say it is going to be cubic, and so on. So the standard form of equation for quadratic equation is ax square plus bx plus c, and we will get a parabolic equation in such cases. Let us start our analysis with the first equation, which is y equal to x square, which is a polynomial equation of order 2, and it is also a power function. So in this case, we can see that because of the even power on x here, that is x square, we will be getting all the positive values for y for different values of x, whether it is positive or it is negative. Together, we are trying to understand what changes we can see if we put a constant as y equal to x square minus 2 as y equal to x square minus 2 or y equal to x square plus 2. So with this constants plus 2 and minus 2, we can see that the graph is either going down by 2 units or going up by 2 units. So the overall nature of the graph is parabolic only, and yes, it is symmetric about x-axis, and yes, it is symmetric about y-axis again, but the only change we can see that it is either going down by 2 units or up by 2 units. One more observation which we can make here is, since these graphs, like the first one, which is h as y equal to x square minus 2, we can see that this function has two zero crossing, one at this point and one at this point. So that means this function has two possible real roots here, and that is something between 1 and 2 and minus 1 and minus 2. So obviously that is going to be plus and minus root 2 here, and these values lies here. Whereas for the case of y equal to x square, we can see that it is touching the x-axis just at one point, that is x equal to 0. So in that case, we can say that this function is having one root that is repeated, so that it is of order 2, and that is at this point x equal to 0. Whereas for the third graph, if we see this function that is having y equal to x square plus 2 has no zero crossing, and if we check the discriminant of this quadratic equation here, we will see that this function will have only complex possible roots, and that is why it is not crossing the x-axis anywhere. So this is when d becomes, that is the discriminant becomes less than 0, so that the roots are going to be complex and it won't have any intersection with the x-axis. Now, in this case, we have made the equation of the form ax square plus bx plus c here, and we can see that from the compared previous question, we have 2x, 2x and 2x here. So overall, the changes we can expect here is the vertex of this parabola has changed at this point and this one. And similarly, we can also see that the line of symmetry has changed. Earlier it was this line, which is y-axis. Now it has shifted to left side because of the roots and because of the introduction of the first order function here. If we try to find the discriminant of this function, we'll see that it will be less than 0. If we try to find the discriminant of this function, we'll see that it will be, the discriminant for this case will be positive, and discriminant for this case will also be positive, so that these will have real roots possible. A function with odd order, that is the power function of the form x cube, x to the power 5, x to the power 7, can possibly have both y as positive value and y as negative value, unlike the power function with even powers like x square, x to the power of 4, which can only have positive values. Now, in this case, we have introduced a constant for the cases like x cube plus 5 and x cube minus 5. So the only respective change we can see that the transformation is either up by 5 units or down by 5 units, but the overall nature of the function remains same. Now we'll talk about the modulus value of a Now we'll talk about the modulus function, which is written as y equal to mod of x. So that means it is checking the absolute value of the function, and the graph of this function can be of The graph of the modulus function will be of this nature, where we can see that on the positive side of x, y will become x, whereas on the negative side of x, y will become negative of x to make it a positive value. So in that case, we can see that this mod value will always be positive whether we go for the positive side of x or the negative side of x. Trying to understand what happens when we add a constant here. So for the general expression that was y equal to mod x, when we add plus 5, this graph is shifted by 5 units above, whereas if it is minus 5, the graph is shifted downwards. So again, we can see that the nature of graph will remain same. Only change we can see that the graph has transformed by 5 units up or 5 units down. Trying to understand that what happens when we put mod x and mod of x minus 4 or mod of x plus 4. So what happens is when you put mod of x, we have it symmetric about the y-axis, whereas when we put y equal to mod of x plus 4, in that case it will shift to the left side, that is, it will be at the center, or the symmetry will be at x equal to minus 4 now, from where we can see that the graph will be moving to the left and right. Whereas when it is h of x equal to mod of x minus 4, the symmetricity moves to the right side from x equal to 0 to x equal to 4. And now we can see that the graph is moving to the right or the left about the symmetricity, that is the line x equal to 4. Next, we will see the greatest integer function, which is represented as y equal to greatest integer x. That means in this case we'll look for the nearest and the lowest integral values which we can have. So let's say if we have got minus 1. So let's say if we have to find y equal to greatest integer for 5.3, in that case it is going to be 5. If we have simple integral value y, if we have simple integral value, it will directly become 5. And for any values on the negative side, let's say if we have minus 0.5, then in that case the integral value lower end will be minus 1, and if it is, let's say, minus 1, then it is going to be minus 1 only. So such function will have a graph of such nature where we can see that there are discontinuity at the integral values, and also there will be a jump in the value which we can clearly see here. For 0 to less than 1, we will have it as so the graph of greatest integer function will be something of this nature. We can see that for x between 0 to 1, the next lowest integral value is 0, whereas when x is equal to or greater than 1 but less than 2, the lowest and next integral value possible is 1. Similarly, when you go on the left side, we can see that for the range of minus 1 to 0, the integral value which is lowest and next to it is minus 1, and similarly it goes down like this. So we can also see that there will be all discontinuities at the integral values, and there is an abrupt or a jump in the integral values. Coming to the next function, that is exponential function, the equation will be of the form y equal to a to the power of x. Now this x can lie between 0 to 1 or maybe greater than 1. So we'll see what changes we can see if we have such values for a. Starting with the graph y equal to the power of x, where we can see that 2 is greater than 1, we can see that starting from the left hand side where the function will be 0, it starts increasing, it will be passing through y equal to 1 when x will be equal to 0, and it will keep increasing at a very high pace. Now we'll see the changes possible when the a value are changed. Now, with different values of a, we can see the change in the nature of this graph. If we see on the positive side of x, we can see that the one which is having the higher value of a, that is the graph y equal to 4 to the power of x, is having the highest slope, or it is increasing with the higher pace, whereas the one which is 1.5 to the power of x, which is the lowest here, is increasing with the lowest slope. Now, similarity which we see on the right hand side will be exactly opposite on the left hand side. On the left hand side, when x will be negative, the 1.5 to the power of x will be having higher values, whereas 4 to the power of x will be having lower values here, because it is 1 by the value of that function. So that will be lesser than that. The possible changes we can observe when we have function of y equal to 2 to the power of x, y equal to 2 to the power of x plus 5. Let's say this is a positive value added. Y to the power of y equal to 2 to the power of x minus 5. So this is a negative value added. So we can see that the function will just be shifted by 5 units up or 5 units down, but the nature of this graph remains as it is. In this case, we will see the changes we can expect when we are changing the a values. Like for the first case, we had 1 to the power of x. For the second case, we have 2 to the power of x. Whereas for the third case, we have 0.5 to the power of x. So we can see that for 1 to the power of x, it is going to be a constant line that will be only 1. Whereas when it is 2 to the power of x, it starts with a lower value and keeps moving to a higher value when we move from a negative value to a positive value. Whereas we'll see the exact opposite nature when it is y equal to 0.5 to the power of x. It starts from a higher value and keeps decreasing when you increase the value of x or when you start moving towards the positive value of x. In this case, we'll see the logarithmic functions where we can represent y as log x with base a. Now possibly this a values can be of different nature, and we'll see what happens when we change the values of a here. Now, in this case, we'll try to understand the nature of log function with the y equal to log x with the base 2. So we can see that in this case, 2 is something which is greater than 1, and the graph nature is something of this form. Now we'll understand what happens when we take a something less than 1. So like the first one, which was the previous case, log x with the base 2, this case is the one where we have log of x with base 0.5. So this 0.5 is less than 1 in this case, and we can see that the graph is going to be right inverted as compared to the something where the a value was greater than a, and something which is now a which is less than 1. So this graph was the one where a was greater than 1, whereas this graph is one where a is less than 1, and we can say that both the graphs are exactly opposite of each other now. In this graph together, we see the logarithmic function and the exponential function together, where a is 10 in this case and a is 10 in this case also. So we can see that log x with the base 10 will be of this nature, whereas y, which is 10 to the power of x, will be of this nature. So this graph has a symmetricity about the line y equal to x. Now we'll see some of the trigonometric functions which we will come across, that is y equal to sin x, y equal to cos x, y equal to tan x, y equal to cosec x, y equal to sec x, and y equal to cot x. So this is the graph of y equal to sin x, and we can see that this is a sinusoidal wave and it is having a periodicity of 2 pi. The one we get on the left side is right opposite to the one we get on the right side, and that is why we also say that it is an odd function where f of x is equal to minus of f of minus x. Now, this is the graph for y equal to cos x, and we can see that whatever comes on the right side is similar to the one which is coming on the left side, and that is why we say such graphs to be even function. Also, this is also having the same periodicity, and that is 2 pi. So, after every 2 pi, the graph repeats itself on left side and right side both. So this is the graph of y equal to tan x, and we can see that this graph repeats itself for every pi time period, and also the graph is not defined at all the odd multiples of pi by 2. That is where the function value takes a very high value, whether it is plus pi by 2 or minus pi by 2. This is the graph of y equal to cosec x, and we can see that the function will take values above plus 1 and below minus 1. It will have no values between 1 and minus 1, as this is just 1 over sin x, and sin x takes all the possible values between minus 1 to 1. So in that case, cosec x will take all the possible values out of the bandwidth of minus 1 to 1. Also, for the case of cosec x, we can see that it is defined for all the values of x except for the values where we will have x to be x equal to the even multiple of pi by 2. Now, this is the graph of y equal to sec x, and we can see that again in this case also the function value will take the possible values out of the bandwidth of minus 1 to 1. And we can also see that this graph is going to be symmetric about the y-axis. So, will be symmetric about y-axis. So whatever we get on the left side of y-axis is same as what we get on the right side of the y-axis. And this is also because we know that cos function is even function, and that makes the sec function also an even function. Now, this is the graph of y equal to cot x, and we should understand that it will not be defined for all the odd multiples of pi by 2. So, it starts from pi equal to 0 to pi, 2 pi, 4 pi, and on the negative side, minus 2 pi, minus pi, minus 2 pi, and so on. So this is the graph of y equal to cot x, and this function will not be defined for all the odd for all the even multiple of pi by 2, such as x equal to 0, x equal to pi, 2 pi, 3 pi, minus 2 pi, and so on. So these are the standard functions which we may come across while dealing with the mathematics required here, and that is what we should know, the basics and the changes possible in the functions of the graph. Thank you.